All right, it's back again. January 21st still, but I'm going to do for 22nd because tomorrow is Saturday. I have the contest, right? I have the contest, so I don't want to do too many tomorrow. And also, I data collection tomorrow, so need to reduce the amount of efforts for tomorrow. So let's do another one today. So this is what is for tomorrow? Stone game. Maybe it's one of the stone games that we've done before. Yeah, we did do it back in October. Okay. All right. Alice and Bob again take turns playing the game with Alice starting first. Initially, there are n stones in a pile. On each player's turn, that player makes a move consisting of removing any non-zero square number of stones in the pile. Also, if a player cannot make a move, he or she loses the game. Given a positive integer n, return true if and only if Alice wins the game. Otherwise, return false. Assume both players play optimally. So if it's 1, it's going to be true. Alice can remove 1. If this, Alice can only remove 1 stone. After that, Bob removes 1. And this is true. Okay. So, do we still go, because it's optimal, do we still do the DFS? I'm going to give a value, right? I mean, the number of moves is 10 to the 5th. Let's just do a square root of 10 to the 5th. Let's see how many potential numbers are there. 316, right? We only have 316 different moves. So all we can do is just, we have moves 1 through 316. And there's no rule to say. So what we can say is basically given a certain number of stones, right? Given a certain number of stones, whether a player can win. The current player can win, right? So I say, I don't know, given like 1,000, right? And then Alice make a move, and then Bob make a move. Oh, we can build. Can we? Do we want to build it up? No, we don't want to. We don't want to build it up. We just give it a value, and then we just pick the largest value that we can move. We'll remove this, and we ending with say 1 stone, and then say Bob wins. All right, and if Bob wins, then the return. Player 1 or player 2. I mean, we can just use -1, right? Okay, we're gonna use -1 to represent player 1, player 2. So what we will ask is, given a value and its current player, is this gonna return true or false, right? So, and then that's gonna be Bob, gonna return true or false, and then it'll be Alice, return true or false. So if it's gonna be Bob, no, I shall return if it's the first player or the second player that's going to win, right? So we do this, and then we return, let's say, return 0 means the first player wins, return 1 means the second player wins. Okay? So we have this, Alice take 1 and throw to Bob. And then this one returns as a 0. Right? So Alice take this move, and Alice wins. And then Alice wins. And if it returns 1, that means Bob wins, so we just keep trying. Right? We keep trying all different situations. Let's try. This should be 22. This for tomorrow, 22. Right? It's for 22. Okay. And we're gonna cache. I'm gonna cache it. Basically, it's just the current number of stones. I don't have two results, right? And from func tools, import cache. So dfs, right? And this is stones, right? And this one will return an integer. Cache just return integer. And lu cache max size equals none. Okay. So all we want to return is if on the return 0, say return 0 if first player wins, right? Otherwise 1. So stone, we give him the stone. That's always the first player comes in, right? So we say that would take from 1 to the end. We just say for I. Now I say I equals 1, right? That's gonna take 1. I'm gonna say while I times I is smaller equal to stones, right? If I times I is smaller equal to stones, what do? We say if dfs stones minus I times I, right? If this one is equal to 1, right? Because this is the next player, right? So next player wins. So if it's 0, it means the next player wins. But if it's 1, it means I win, right? I win. So if it's this, then I return 1. That means the first player can win. No, return 0 means the first player wins. Otherwise, if it's equal to, so I just say if this, then I'll return 0. Otherwise, which means this one equal to 0, which means this player wins, the next player wins. So which means if I pick this, I'm not going to win. Then I'll say I plus equal 1. I'll try the next one. And then blah, blah, blah. If like none of this, I win, right? If none of this, I win. Return 0. No, return 0 if first player wins. Otherwise, return 1. First player does not win, right? So if first player does not win, okay, say return 1 if first player wins. Otherwise, return 0. How about true and false? How about true and false? Boolean. We return true. Wow, it looked great. Return true if the first player wins. Otherwise, false, right? So we just say, if this is true, then I lose. So we say if not, which means the second player does not win, I win. Then I return true. Otherwise, return false, right? And then we just return DFS stones. Okay? We have very, very simple test cases. It's so simple that it's not helpful at all. 2 will be false, and 4 will be true. It's just very simple test cases to start with. And this one will be winner of this. And yeah, it will pass, but the real challenge is we come in here, right? And then we're gonna throw in some just random values. I don't know. I just smashed my keyboard. And then 1, 2, 3, 4, 5. All right, so we put in some random values. Not really that random, but just a couple of values. And I think we might have it. All right, give it a run. And the result is we have passed. Okay. We passed, but let's take a look at the result previously. And look at this, 161 megabytes. The memory usage is horrendous. Like horrendous. Let's write our analysis. I mean, I don't know, like maybe we take not from one, but from the top down. Not from top down. Take, I don't know, minus one, and a minus one, minus one, minus one, minus one, minus one. I don't know. So yeah, maybe I'm just write it down first. So this is LeetCode. I like this question because I can solve it. All right. So we say since there are only 316 different moves, only in the worst test case, we can afford to actually it's not right. Stones minus this, yeah, we can afford. No, it's actually it has nothing to do with that. It's just yeah, that's actually not true. So okay, so this one, the idea is how should we summarize the idea? The idea is the remaining number of stones can be considered as a state. We can cache the result as given a number of stones, right? Can the first player win for all possible stone conditions, right? For all possible stone conditions. So that is our idea for all possible stone conditions, and we cache it, and this is the result. So during the DFS, right, if this during the DFS, we are always standing, we are always looking from the perspective of the first player. And then when we recursively call DFS again, its result indicates whether the second player will win. Thus, if the recursive DFS call is true, we have to try the next value for the first player. Otherwise, we know that the first player has already won. Time complexity. I don't know. I'm always bad at estimating time complexity for this. What's the time complexity? We have this amount of stones, and then every time I can have that many different choices, right? Each time I have all these choices. I have square root of n number of choices. And then, I don't know the time. I have to check my answer. So that is the runtime milliseconds with terrible space memory requirement. 161 megabytes. All right, so this is what I have last time. This is what I have this time. It is terrible, 18% ranking. So this time, even if we cached. All right. So is this the bottom up? Yeah, this looks like a bottom up. Maybe bottom up is faster. Okay, I didn't read it, so let's try it. This is top down, all right? We can definitely try bottom up. So the bottom up, we'll go one by one. All right, I'll go one by one. How do we do this? So the bottom up is the same idea of number of stones, right? First player will be true, and this was the first player play this, and we can go. How do we do bottom up? I'm gonna try every single thing, and then if any one of them, right, it returns a true. So let's just say if my first player play this, yeah, it's the same idea. So bottom up is the same idea. I'm not sure if it's gonna be faster. Maybe it is faster. So this is, let's say, same idea as solution one, but bottom up. So first wins equals false times n plus 1, yes. And choices equals 1, I times I for I in range. So I don't want to use math, so I feel that's unnecessary, but maybe I need to. That's just simple math. In range 1 towards math.qrt and well, this one will give me a number, right? And I want to do int of this number and plus 1. Okay, these are the choices. So we just say for, I actually say first wins 1 equals true, right? And we just say for I in range from 2 to n plus 1, right? 2 to n plus 1. I don't know if this, so we're gonna say for choices in choices, right? If choices is larger than I, that would break. Otherwise, if it's larger than I, oh, hold on. We can go through the entire thing. Let's go through the entire thing. So we can just say first wins for C in choices. I'm gonna say first wins shall equal to, right, C in choices if C is smaller than, if C is smaller equal to I, right? So 1 is true, first win 0 is also true. Well, in this case, I can do this, and then we can just go from 1, right? If c is smaller, you go to I. And then we say choices, choices. First wins I minus c, right? I minus c for this, right? I minus c. Oh, hold on. First move, right? So for 1, I got a first move. That's actually the second move. So 0 shall be false, which means I don't have to do anything, right? So not, right? So if it's a false, we want everything to be false, right? We want everything to be false because that will be the second move. The second move has to be false to guarantee the first move true. So we're gonna do this or not this, and we're gonna say all of them has no any of them is true, right? So this just becomes this, and then we return first wins n. It's not subscriptful. First wins. First wins I. Okay. Let's try this. $1,028. Well, this is faster. Yeah. Much faster. Alright, now I'm going to check the result. SQRT. Yeah, that's exactly what I expected. Yeah, so this is bottom up. Bottom up. This is much faster than recursion, than a top down, And we can actually see the runtime, right? So the runtime is O SQRT O. It's actually ON. Wait, is it ON? That choices we have is QRTN. So it's N, so that's N, times SQRTN. And this one runs as 1292 milliseconds, or a 57% ranking. Alright, so we're doing pretty well for this one. Now, this one is not that hard. DFS with memo. Yeah, I'm gonna use LO cache. Yeah. Memoization. That is true. Ah, yeah, I should try. Guess I already have SQRT, so why not? Alright, so this is same as solution 1, but start from bigger choices, going down. Okay? So I equals int SQRT stones. Alright, so while now this won't be, while I is larger equal to 1, and now we do I will be minus equal 1. right? So solution 3, name is QRT. Now having math dot is QRT. Okay, let's see how fast this can go. All right, code. Oh yeah, it is fast. Oh wow. Oh wow. So this is 10 times faster than from small to big. It's 302 milliseconds. It's also faster. It's also faster than the bottom up solution. 85% ranking. Yeah. Ooh-wee. Good observation. I wonder why. Hmm. Interesting. Should have tried this one. Yeah, should have tried this one. Alright, anyway. So that's that. And we have time to spare. So let's work on this. Heaters. Winter's coming. Ooh, winter's coming. Winter's coming. That's how they say it, right? Winter has come. During the contest, your first job is to design a standard heater with a fixed warm radius to warm all the houses. Every house can be warmed as long as the house is within the heater's warm range. Given the positions of houses, I have the houses, and the heaters on a horizontal line, return the minimum radius standard of heaters so that those heaters could cover all houses. Note that all the houses follow your radius standard and the warmth radius will be the same. 2, when a heater was placed in the position 2, and if we use radius 1 to cover everything. Now this one had position 1 and position 4. It's still 1. The 2 heaters was positioned in 1 and 4. Hold on. Position 1 and 4. Nah, it's 1 based. Jesus, come on. Why you use 1 base? 1 and 4, right? So houses, what is this? This is the coordinate? The position of that, that's the position. Ah, that's the position. The position of 1, 2, 3, 4. When there is radius 1, then and for this position, heaters is 2. Ooh, that is a good test case. We have 1 and 5. 1, 2, 3, 4, 5. Right, we have 1 and a 5. And we have a heater at number 2, so we need 1, 2, 3. That makes sense. Good question. I don't know why people don't like it. I think it's good. I think it's a good question. So, okay, let's think. I can pick up all the positions, right? If I pick up all the positions of the houses, okay, I have all the positions of the houses and the distance between them, right? All the distance between them. And then I get the heater position, okay? If I get a heater position, right? If I have only one heater, and then that will be simple. The minimum range will be the house that's furthest away from it. So if we have the houses all sorted, right, and we can do a binary search to know where it will land. And we just, we don't even need a binary search. We just either left or right, right? Okay. So what if I have multiple? If I have multiple heaters, let's say we have two heaters, right? If we have two heaters, and it depends on where the heaters are positioned, right? If the heater is positioned outside the house range, or inside, or some outside, some inside, and every heater has the same range, keep in mind, every heater has the same range. So all we need to find out is the largest among all the heaters, right? Okay. So are you saying that the largest zone is not really largest because two heaters, their range like increase in the middle? Mm. So one heater, we drop the heater there, right? And then we can compute the maximum range it requires. Say we drop it here, so I require that much. And I drop the second heater. And when the heater drops, right? And if with the heaters also, we sort it, okay? We sort the heater positions. I'm not sure if it's sorted, but we just sort them. The houses and the heaters, or both, we sort them. Now, after we sort them, we go to the second one. So we know the second one must be to the right, right? Now, if it's to the right, then we know the first heater will take care of, let's say, everything to the left. The first heater will take off everything to the left, right, and everything to the right, whatever. It's just, you're going to create a maximum value between the two. And the second one comes in, and what I know is that if I want to take care of the houses on the left, then I will have to expand more range. So the first one can handle it, right? So I don't have to. So all I need to worry about is the houses on the right, right? The houses on the right. But it could be, so I worry about the house on the right. So I find out the maximum I towards the right. And now the first one, so when a new one comes in, right? A new one comes in, and what we need to figure out is, so the first one has to handle the left. So when the first one comes in, and we find out how much is to the left, right? We get this value. And the second one comes in, and so we got, so to the left and to the right. So it'll be two values, right? Two values. One is to the left, one is to the right. And then the second one comes in, and it will have a new to the left and to the right. So to the left will be helping the first one to cover the things in the middle. Okay, so hold on. So the second one comes in, right? When the second one comes in, because it's to the right of the first one, so first one's right doesn't have to worry, right? Okay, first one on the right doesn't have to worry. So when the second one comes in, we need to find out the radius required. How do we find out the radius required? So we have the second one comes in, and the radius required on the right, we get a value. The radius in the middle, I get a value, which is, right, how do we find out? Yeah, how do we find out the radius in the middle? the radius in the middle, we find out if there are houses in the middle, right? If there are houses in the middle, so there's also a condition that there might not be houses in the middle. If a new one comes in and there is no houses in the middle, then yeah, we just consider if there's no house in the middle, then we don't consider this, right? And then we have on the left, or the first one will be on the left. So we have a value, we have this value, then we compute the bigger of the two, right? The bigger of the two, because we need to cover everything, okay? So we consider the bigger of the two, so we have this. Now if we have a third heater comes in, right? The third heater comes in, and then we know the first two heater, we get the minimum radius, we find out. So when the third comes in, right? When the third comes in, and let's say when a third comes in, it has to care for the right, right? It cares for the right, and that would definitely be smaller, right? And then it's smaller. Can the first one do? Yeah, we can. It depends, right? Should be like just to the left, the right, and the intermediate, right? Intermediate length. So we say to the left has a certain value. Intermediate is if there's nothing in there, it will be 0. If there's something that we find out, and then to the right we have a value. So every time a new come in, we'll break the right. Right? We'll break the right. We'll get a new right. We'll get a new intermediate. So we have a new intermediate, and an old intermediate, and all of these are the same, right? Oh, they're not the same. They're just intermediate. The minimum intermediate, the minimum left, the minimum right. Now we pick the largest among them, right? So when a new thing comes in, I'll produce a new right and a new intermediate. So we have 1, 2, 3, 4, 5 of a new value, right? And we need to find out the biggest among them. Yeah, does that work? Every time we get a new one, we produce 2 more values, right? We produce 2 more values, and we break one value, and then we get 2 more values, right? And then we have the biggest at the top. We get a biggest at the top. No, not biggest at the top. So we have this value, right? So we can pop this value, push 2 more in, pop this value, push 2 more in, pop this value, push 2 more in. And once we're done, we just find the maximum among them. Yeah, I think this might work. This might work. And what if the starting position is to the right, to the left? Oh yeah, that's just we don't. Yeah, it might work. All right, try it. I think it might work. It might work. 75. Seriously, I think this might work. All right, so what we want to do is we want a minimum radius, radii, right? Radii. It's gonna be this, right? And oh, it didn't say if they're sorted. Yeah, we just say houses dot sort, heaters dot sort. Okay, we sort them, and from bisect import. Right? Okay. So what we're gonna do is what we're gonna do is, oh, still we haven't solved everything, right? So the heater will get in, so we know where the heater points at. And if we know the previous heater's location, if we know that, that will be very helpful, right? That will be very helpful. If I know the previous heater's location, not really the location. Yeah, I know the previous heater's location. I want to know if there's any in between me and the previous heater. Um, how do I know that? If I know the number of houses, so every heater comes in, I know the number of houses to the left, right? If I know that, if I know that. Hold on, can we decide to do say 3, 2? I don't think this is legal. It's fine. It's fine. So I need houses sorted. Nah, I need to avoid these type of situations because then the number of counts will be wrong, right? We'll have now it cannot have it repeats. Let's see. Let's not worry about that, right? Let's not worry about that. I mean, this one just says it can handle repeats. Right, I think this would just say it can handle repeats. Yeah, it just says it can handle repeats. Okay, so we have these positions, right? So now it comes in, and I know how many houses is to the left. And then a new one comes in, I know how many houses. No, that's not what we want. What we want to know is the actual position, right? Is the actual position. So when it comes in, we want to know the actual position, okay? Because if I have houses in between, right, and then current one already the minimum, which means well, it's covered to the right, right? It covers to the right, and now I come in, right? Now I come in, and I know this position, and I need to know what positions are the houses in between the two heaters. Because I can come in, I can binary search, say, okay, I'm going to be in this position, right? And in between houses. And the previous one, I need to know its position, right? Its position, like the position that it should be at. The position it shall be at. And then, oh man, then its position, and then with me, right? With me coming in, I need to figure out how, the positions of the houses in between us, right? In between us. And I want to reuse. So the previous one, the position, not really the position. We can say the index, right? The index in houses where it's going to be inserted. Okay, so it's in here, and then we check if it's the same. or if it's not the same. If it's the same, if it's not the same, and I have me, then I have uh, my location, right? I have my location, right? Or my location. So I have my location, I have the previous location. If it's in the middle, it's going to be in this one. We attach to the left, right? Actually going to be attaching to the left. So it's going to be this position. If this, it's actually attach to the left, to the right. So no matter what, we're just going to do -1. So I attach to the left, right? So if I attach to the left, the things in the middle is not covered, right? Not covered. And then we have 2. So we need to find a radius, the minimum radius to cover them all. What is the radius to cover them all? Like I have these values, right? So we can do one of them, right? And then we just extend it one time, and we extend it one time, and if there's one in between, then just the smaller of the two, right? If there are 2 in between, so one time shall be the bigger of the two, right? If there are 3, we go one time, and then 2. So yeah, so they both extend. They both extend until the cross, right? They extend. Well, we need to find this if it's even number. So just extend, 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 right? And then we find the bigger of the two. If it's odd, then extend, 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 and we find the also the bigger of the two. Wait, no. If there are even numbers of houses, right? So on both sides, when extend, extend, so they will never cross, right? Then we just pick the larger between the two, and that will work, right? The larger between the two. Would it be this? Add this is actually smaller than this. It's possible. Like this one can cover all 3, and this is smaller. So what? So from this position, I need to so I just keep extending. Just keep extending until we encounter everyone. Okay, let's do. Oh my god, I don't have a good idea how to find the minimum. Yeah, because if the houses are like on one side, then that will be enough, right? So you can go one side cover everything, the other side cover everything. Okay, so that's like all covered. So let's say for this one, need to cover one house, right? And this one we use the same. Say, can it cover that? Right? Say it cannot. So each one cover one, right? So okay, each one cover one, and then um, if there's only 2, then that's at the end of it. If there's 3, then so we just extend, extend, extend. We extend the entire thing, so we have all these values. And from the other side, extend, extend. We have all these values. So what do we do? Yeah, what do we do? how do I know how many the radius to cover the middle? So it's on the left side. If I cover 1, right? And on the right side, I say I cover 1. So the radius to cover 1. So the radius if I cover 1 and on the right side also cover 1. So like if I cover 1 and the right cover also 1. So we try to make it optimal. So left cover 0, right cover everything. So we have a value, right? And then left cover 1, right cover 2, right? We just sliding window, right? Sliding window. So we go through all scenarios, right? All scenarios. And then for each scenario, we're going to pick the larger of the two. Now we find the smallest of them. Okay? We find the smallest of them. So that will be the new thing for this. Okay. Okay, this might work. This might work. But for this to work, I'm assuming I shouldn't assume. So I don't know. Yeah, it should be houses. I say sorted houses equal to sorted set houses, right? And then this one, same thing, sorted heaters equals sorted set heaters. All right, so when we do this and we have the minimum radii for everything when it comes, right? So what do I do? So if I'm on the left side, right, most left side, so we just need to cover the entire thing. We'll still do binary search, right? Binary search, and we have its position. It's going to be 0, right? If we go on be on the left side, it'll be 0. And if I'm 0, then I just cover the entire thing. And then the second one come in. If it's also 0, so in between, is that their position? Position, and also it's index relative to houses, right? It's index relative to houses, and if there's nothing in between, so that's just going to be 0, which is a push. So we pop 1, right? Push a 0 in, and then we get a new one, right? So if it's 0, and if it's nothing on the left side, what will be on the left side? So we need to find something on the left side, right? Find something on the left side, and then the radius will be, let me see. The radius will be, if I have this, just this minus this, that will be the radius. And for me, if it's going to be 0, then the left side will be 0, and then the radius will be negative, right? If it's a negative, that's going to be 0. Okay. Okay. So what we're going to do is for heater, heater in. So I'm going to say pre-position, pre-index 0, doesn't matter. So for I, heater enumerate. Do I need to enumerate? I don't. I think I just go heater in heaters, right? And then index will equal to bisect right houses and heater, right? So whatever comes out, we always want to whatever comes out is in between, like it's in this position, right? It's in this position. And when I'm in this position, I want to know based on the previous one, right? Based on the previous one. So that actually it should be 0. So you always want to pop first. So pre-index and this. So index, right? And then we always pop it. So we always say dot pop, right? And then we're going to put something else in. And the something else depending on the previous index. So the previous index and my current index. And we say if the previous index and my index, that index relative to houses, right? And if in between our indices, and where does this index pointing at? This index we shall be pointing at, right? We shall be able to pointing at the ones that can be covered, right? So it's in between, so it should be -1. So which means this should be -1, right? So index will be always this -1. We're always -1. That's the index that I'm going to record. That's the index. So be here, right? The smaller one. Okay. So now I got my new index coming in, and a new index is going to be this and in between these two. So I'm going to go, boom, we'll go -1. Okay, we'll go -1, which means it's going to be from the previous, right? Previous to the right. So be larger than the previous and smaller equal to the current. Okay, larger than previous but smaller equal to the current. These are the ones that we need to include, right? We need to include. And we have the index, now we have the previous index, right? Now we're just gonna do the minimum. So the minimum minimum between, right, equals math.inf, safest, right, import math. So minimum between. So minimum between equals this. I mean, it's for I in range, right? It's gonna be pre-index because we need to include the. Or do we include the pre-index? We do not. We do not, because we do this and then we do -1, right? So this is included to the left, right? This is included to the left. We don't include that, so it's going to be pre-index +1, right? All the way to index +1, right? All the way to index plus. So pre-index +1. So index is this, right? And then -1 is this one. So we want to include this. So it's index +1. So we're going to do this. For each one of them, we can get houses I. Houses I is the position. Okay, houses I is the position of the house. So now the between value is going to be the maximum of the with a previous heater and a current heater, right? So it's going to be, so this is previous include, right? So this is the houses that gets included by the previous. So it's going to be the previous include, that's the index of the house, minus the previous heater position. So it's going to be heaters I minus 1, and it's going to be the current heaters H minus the current include, right? So in the between is just find the maximum. So between is the maximum of these two, and a minimum between shall be the minimum of minimum between and this maximum between every single time. Okay. Alright, so when we go through this, we get the minimum between, and say minimum radii dot append, right? The minimum between and minimum radii dot append to the right, right? So current heater, when you go to the right, and then we have the index. I don't need the index; it's just the rightmost, right? Rightmost, and the rightmost shall be the rightmost. So it's just houses minus 1 minus, right, minus the current heater. And then I'm going to take a maximum of this and 0. All right, and then we just keep working on this, and then we're going to return the maximum of the minimum radii. Okay, let's try this. We have 3, shall return 2, 1, 1, 2, 3, 4, 1, 4, return 1, 5, 2, return 3. Alright, so no matter if it's passed or not, we are going to AND this because it's passing 1 hour. Houses, heaters. Int object is not iterable. Oh, it's not houses, it's, oh my god. All of this has to be sorted. Shoot. Alright, I'm just gonna end it here. Okay. See you guys tomorrow.